Welcome to Quantum Realms Explained, where we demystify the most mind-bending concepts in physics. Today, we're diving into black-body radiation and Planck's quantum hypothesis, a pivotal moment that reshaped our understanding of the universe. This phenomenon paved the way for quantum mechanics. So, what exactly is it? Imagine a hypothetical object that perfectly absorbs all electromagnetic radiation that falls on it, regardless of frequency or angle. It doesn't reflect any light, which is why it's called a black body. When this black body is heated, it emits thermal radiation. The spectrum of this emitted radiation, that is, the intensity of light at different wavelengths, depends only on its temperature, not on the material it's made of or its shape. Classical physics, based on the laws of electromagnetism developed by Maxwell, attempted to explain this observed phenomenon. However, it ran into a serious problem when trying to predict the intensity of radiation at higher frequencies. This problem became famously known as the, quote, ultraviolet catastrophe. Classical theories predicted that a black body should emit an infinite amount of energy at ultraviolet and shorter wavelengths, which clearly doesn't happen in reality. Here, you can see a comparison between classical predictions and experimental results. Classical theory, the Rayleigh-Jeans law, works well for longer wavelengths, but diverges dramatically at shorter, higher frequency wavelengths. The failure of classical physics to explain the observed blackbody spectrum indicated a fundamental flaw in the classical understanding of how energy and light interact at a microscopic level. It was a crisis for physicists at the turn of the 20th century. In 1900, Max Planck proposed a radical idea to resolve the ultraviolet catastrophe. It was so revolutionary that it laid the foundation for an entirely new field of physics, quantum mechanics. Planck's bold hypothesis stated that energy is not continuous, but rather, it is emitted and absorbed in discrete packets, or quote-quote quanta. Think of it like a staircase, where you can only stand on individual steps, not in between them. He proposed that the energy of each quantum is directly proportional to its frequency, expressed by the formula E equals hf, where E is energy, F is frequency, and h is Planck's constant, a fundamental constant of nature. This simple yet profound idea allowed Planck to derive a formula that perfectly matched the experimental black-body radiation curve across all wavelengths, finally resolving the ultraviolet catastrophe. By assuming that oscillators in the black body could only have discrete energy levels, Planck's formula naturally suppressed the emission of very high-frequency, short-wavelength radiation, aligning with observations. Planck's quantum hypothesis marked the true birth of quantum mechanics. Although Planck himself initially considered his quanta to be merely a mathematical trick, Albert Einstein later used this concept to explain the photoelectric effect, solidifying the reality of energy quantization. The implications of Planck's work are immense. It fundamentally changed our understanding of light and matter, moving physics from a continuous, deterministic world to a discrete, probabilistic one. Planck's constant h became a cornerstone of quantum physics. It governs the behavior of particles at the atomic and subatomic levels. From lasers and transistors to medical imaging and quantum computing, the principles derived from Planck's initial hypothesis underpin countless modern technologies. In conclusion, blackbody radiation and Planck's quantum hypothesis represent a monumental shift in scientific thought. It showed that the universe operates on principles far more intricate than classical physics could describe, revealing a fundamental discreteness in energy that had profound consequences. This breakthrough not only solved a puzzling problem, but also opened the door to the quantum revolution, forever changing our perception of reality. Thanks for watching Quantum Realms Explained.